So that was it about Euler's method. Next thing that we're going to look at is we are still solving first order ordinary differential equations. But we are using now what is called the Runge-Kutta method. Okay. So what is this method? It's basically a generalization of Euler's method. And it's not one method, it's actually a series of methods. You can have first order Runge-Kutta, second order Runge-Kutta, third order, fourth order, and so on. And what I mean when I say that it's a generalization of Euler's method is that Euler's method is basically just first order Runge-Kutta. So what we are going to discuss over here is second order, and then I'll say a few words about the fourth order Runge-Kutta because that's the one that's used most often. So what exactly is this method? Let's draw a graph. So t, x. Suppose this is the function that we are trying to find. So let's say initially I am at some time t. What Euler's method says, so t, and I know what is the x at that t. Euler's method says that I want to find out what's happening at the next step at t plus h. So I want to find this value. That is the point of doing Euler's method. At every step you want to find out what is the next x. So Euler's method says that the next value of x, so x at t plus h, is just xt plus h times the derivative. The derivative at t and x. So that just means you're taking the slope at this point, tx, and you're saying at t plus h, what is the value of that? You're saying that this is the required value of x at t plus h. So obviously that's wrong. This is the amount of error that is there in our estimate. But that is as good as Euler's method gets. You can't get better than that. It tells you to go to the next step depending on the slope as calculated at this point xt. What Runge-Kutta says, so let's say this is Euler. Runge-Kutta says you don't take the slope at this point xt, you take it at the midpoint of t and t plus h. So you take the slope over here. So what is the slope at this point? Slope at this point is something like this. And it says you now starting from xt, you use that slope to estimate what is going to be the next value of x. So now in this case the error is just this much. Can you see? Probably not. So over here the error is just between the white and the pink over here. That little step over there, that is the error coming from Runge-Kutta. So this is Runge-Kutta second order, RK2 let's call it. So as you can see, by taking the slope at the midpoint instead of at the initial xt, you are reducing your error considerably. So that is the basic philosophy of Runge-Kutta. Of course, question is, we don't know this pink point over here because I mean the reason we're doing this is to find the function. So I don't know where exactly this point lies. So to estimate where this point lies, I will still use Euler. So I will do it over here. So that will introduce a little bit of error in the calculation, but that's still much better than doing it by Euler's method. So let's write this down mathematically. So we are going to use the midpoint of t and t plus h. So that is, we are going to do it at t plus h by 2. So let's write down the mathematical formalism for this. I'll use the next page. So if I want to write down x of t plus h, so let's write down the Taylor expansion, but let's do it slightly differently. I'm going to write this as x of t plus h by 2 plus h by 2. So I'm going to treat this as my a and this as my delta x, if you know what I mean. So this is, so I'm going to expand, I'm going to do my Taylor expansion around this point, with this being the small variation. So this looks like x of t plus h by 2 plus h by 2 times dx by dt evaluated at t plus h by 2 plus 1 over 2 factorial h by 2 square d2x by dt square evaluated at t plus h by 2 plus so on. And if I want to write x of t, I'm going to write this again as x of t plus h by 2 minus h by 2. Once again, I'm going to do a Taylor expansion. So x of t plus h by 2 minus h by 2 dx by dt at t plus h by 2 plus 1 over 2 factorial h by 2 square second derivative at t plus h by 2 and so on. Now let's take the difference of these two. So x of t plus h minus x of t. You will notice that the first term cancels out. The third term also cancels out. You're only left with the second term, the fourth term, and so on. So only the even terms will remain. So this becomes h times dx by dt at t plus h by 2 plus order of h cube, or in other words, x of t plus h is x of t plus h times f at x of t plus h by 2 t plus h by 2. So this just comes because of, that's basically the differential equation. Our differential equation we're trying to solve is dx by dt is f. So I've written dx by dt as f over here. So by using the midpoint of t and t plus h, you will notice that now our error is not of order h square, it is of order h cube. So this is one order of magnitude better than using Euler's method. So that's why we prefer this Runge-Kutta. So this is Runge-Kutta. Did I specify somewhere? This is second order Runge-Kutta. and that gives us an error of order h cube. Of course, it means that we have to calculate the function at t plus h by 2, which we don't know in principle what that is, but we can estimate it. And to do that estimation, we will go back and use Euler's method. So first order Rumikuta. So we'll first use Euler to estimate what x will be at t plus h by 2, and then we plug it in this formula, which will give us our second order Rumikuta. So in terms of programming, the steps will be as follows. Let me write it from here. So first we will define something called k1, which is h times f of xt. Then we will define something called k2, which is h times f of x plus half k1 t plus half h. And then x of t plus h is x of t plus k2. So this is your step-by-step way. Given an x of t, this is how we will calculate x of t plus h. And then you keep doing this iteratively multiple times, and that will give you the function that you are looking for. So this is your second order Rumikuta. And then you can proceed further. You can do a third order Rumikuta. Basically, what's happening at each step, at each order of this Rumikuta method, is your procedure becomes a little more complicated, a little more involved, but your error keeps reducing each time. So it's a compromise between having a more complicated program and having a more accurate program. So you choose what you want. Normally, for most applications, for most scientific applications, people prefer to use the fourth order Rumikuta method. Because this has a good balance between being accurate and being complicated enough that it takes a little extra time. So this is a good balance, or a good compromise between these two requirements of speed and accuracy. How does fourth order Rumikuta work? So over here you define a k1, which is h times f of xt. Then you define k2, which is h times f of x plus half k1 t plus half h. Then you define k3, which is h times f of x plus half k2 t plus half h. Then you define a k4, and then finally your x at t plus h is x of t plus 1 over 6 k1 plus 2k2 plus 2k3 plus k4. So this entire thing is one step, one iteration. When you're given xi, if you're trying to find xi plus 1, you have to do these 4 or 5 steps. So that gives you xi plus 1. Then from I plus 1, when you want to go to I plus 2, again you have to do these 5 steps. So you keep iterating this over and over again, and you end up with your solution. So fourth order Rumikuta is very good, gives you sufficiently accurate results in most cases. Okay, so this was about ordinary differential equations in one variable. In principle, you can have differential equations with multiple variables. For example, you might have something like dx by dt is equal to, so you have two variables, x and y, two dependent variables. So let's say this is x plus y, and this is sin x times y cube, just to give you an example. So these are called coupled ordinary differential equations. And these are two variables that are coupled to each other. So important thing to notice over here is that the rate at which x is changing depends not only on x but also on y. And the rate at which y is changing similarly depends not only on y but also on x. So if over here, if this equation did not have a y dependence, so if I got rid of this, and if this equation did not have an x dependence, so suppose this was not there, then these would just be two independent differential equations. One is a differential equation in x, one is a differential equation in y, and you know how to solve it. You've seen Euler's method, you've seen Runge-Kutta method, so you can use one of them to solve this. But now that is no longer the case. There is an x and y dependence in both of them. So how do you do this? So you have to generalize what we have learned from Euler's method or from Runge-Kutta method. So in general, the problem that we are trying to solve is dx by dt is some function fx of x and y, and dy by dt is also some function, let's call it fy of x and y. Actually, why only x and y? It could also have a t dependence in it. So these are your coupled ordinary differential equations. And over here, I have only written in two variables, but there's no reason why you have to stop at two. In principle, you can have x, y, z, x, y, z, w, whatever. As many as you want. You can have as many dependent variables. So you'll have those many coupled ordinary differential equations. Okay, so how do we attack this problem? Well, instead of treating our dependent variables as individual variables, we'll treat them as vectors. So why don't I define a vector R as having components x and y, and I will define a vector f as having so f of r and t, because f depends on x, y, and t. So this is going to be the vector fx of x, y, t, and fy of x, y, t. So these are my r vector and my f vector. So then the differential equation, I can treat it just as one ordinary differential equation, but in terms of a vector, not in terms of individual x, y. This differential equation becomes dr by dt equals f. So this is the equation that I want to solve. Now it turns out that whatever methods we learned before, whether it's Euler or it's Runge-Kutta, you can use the same thing also for a vector case. So just to give you an example, well, we'll do both. So if you're looking at Euler will say that R at t plus h is R at t plus h times f of R t. So if you go back and look at the previous pages in your notes, you'll see this is exactly the same thing that we had for Euler in one variable. So same technique works. You basically, instead of having one variable in your program, you will have an array of 2 or 3 variables depending xy or xyz. And in your program, Python allows you to do operations on arrays as if they were individual variables. You can multiply, you can add, etc. So exactly the same way you will end up solving multiple equations simultaneously, and it will work out. Or if you're interested in doing Runge-Kutta 4, fourth order, then how will you do it? So then you will define a k1 vector, which is h times f of rt. Then you will define a k2 vector, which is h times f of r plus half k1 t plus half h. Then a k3 vector, exactly the same way as we've been doing before, and a k4 vector, and then in the end your r at t plus h will be r at t plus 1/6, 1 times this, 2 times this, 2 times this, 1 times this. So this is your fourth order Runge-Kutta method for coupled differential equations. So so all of these vectors k1, k2, k3, k4, r, f, they will have as many elements as there are dependent variables in your ordinary differential equation. Okay, so that's about differential equations with multiple variables. Now, so far we have been dealing only with first order differential equations. So we only looked at differential equations which are of the form dx by dt is equal to something, some f of xt. We have never looked at anything that has a second order derivative or a third order derivative and so on. So let's look at these now. It's higher order ordinary differential equations. So the trick is to always reduce them to first order. What do I mean by that? Suppose I have some differential, suppose I have a second order differential equation. So d2x by dt square is some function of x dx by dt and t. So what I will do is I will define dx by dt as some y. So let's call this equation 1. Then my second order differential equation just becomes dy by dt, because dy by dt is d2x by dt square. So dy by dt is some f of x, y, t. We call this equation 2. Now you will notice that equations 1 and 2 are just coupled first order ordinary differential equations in x and y, right? So this tells you dx by dt in terms of y, and this is dy by dt in terms of x, y, t. So these are just two coupled equations, and we have seen before on the previous page we saw how to solve coupled ordinary differential equations. So you use these techniques over here to solve both of them. So you will get from this one, so you will get some solution for x and you will get some solution for y, and solution for y means this is just dx by dt. So if you know y, having solved this differential equation, then you can again solve it and get x. Basically these are two equations. You need two conditions. So number of boundary conditions required is equal to the number of is equal to the order of the differential equation. So when we had the first order differential equation before, we only needed one boundary condition to solve it. Now in this case, we will need two of them. So you will have to specify, for example, x at t equal to 0 is something, some x0. And you also have to specify dx by dt at some t equal to 0. Let's call it some v0. So these will be your two initial conditions, and those will go into solving these two differential equations that we have. Similarly, of course, here we only took second order as an example. You could also do it for a third order differential equation. Suppose I had something of the form third derivative is equal to some function of x, first derivative, second derivative, and t. So how would I go about solving this? I would define first of all dx by dt, I would call it y. Let's call this equation 1. Then I would call dy by dt as z. Let's call this equation 2. So remember, z is d2x by dt square. And then d3x by dt square would by dt cube would just be dz by dt. So my actual differential equation becomes f of x, y, z, t. So this is my equation 3. So now 1, 2, 3 are coupled differential equations. And once again, you can solve these using the techniques that we have learned before. So this is a general way of approaching how to solve higher order derivatives, differential equations which have higher order derivatives.